So f of 2, so this is a piecewise function, right? This warm-up will sort of warm up our brains. So remember what we did yesterday. Remember we cut up the functions and made piecewise functions from them. And then it will lead us into today's lesson where we are going to evaluate and graph piecewise functions. So this asks us to do two things. One is find f of 2. This number inside the parentheses at 2, is that an x value or a y value? When it's inside, it's an x. And so it's basically saying, okay, when x is 2, what is the y, the corresponding y value there? So here's where x is 2, and you find where the point on the graph is that goes with that. So it's up here, da, 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 da. It's right here, but we want the output for that input. What's the output for the y value? It's 6. So f of 2, the answer is just 6. You don't even have to do any math. And then for f of 6, oh, and by the way, this piecewise function is made up of two different kinds. This one right here, this straight one, what kind of function could that be? What parent function? You got two choices it could be. Could be linear or absolute value that's been cut off at a certain domain restriction, right? What about this second piece? What does that look like? Quadratic. So when I just found f of 2, was that in the domain for the linear or the quadratic? The linear, right? The linear. So now I'm going to find f of 6. Which piece does that belong to? The quadratic, right? So it's right here. And when I trace up, it's in this piece, the rounded piece. So it's part of the quadratic. And what does y happen to be there? 4. And then I have one other question for you. Is there a value at f of 3? Is there a value at f of 3? Yes, right? Does that value belong to the linear piece or the quadratic piece? Not both. The linear, right? Remember this little half circle right here? So here's where f of 3 is, right? Here's the point. Y is 4. So the answer is 4. But then I asked you, does it belong to linear or quadratic? The closed circle is part of the linear. This open circle that's part of the quadratic means it's not defined right there at the 3. It's an open circle there, okay? So that part belongs to the left side. And those are some things we're going to be thinking about again today for today's lesson. So let me get you your notes. By the way, we have a quiz coming up on Tuesday. It's going to be over. So here we have this lovely piecewise function, okay? No graphs. We're going to be finding the value. We're evaluating, but using algebra, okay, instead of just looking at pictures. So it's made up of 3 pieces. So remember, that's what a piecewise function is. One function made up from parts of other functions. So what I'm going to do is put some color here so we can talk about it a little bit easier. It's got this red part, this green part, and this blue part. And then we've got 5 problems that it's asking us to find. H of negative 3, h of negative 0.001, etc., etc., etc. So we're going to start with h of negative 3. And here's how you do this. This is an x value, right? X is negative 3. We have to figure out which piece of the graph that belongs to. So we go look at the domain restrictions over here. And we have to figure out which one of these does negative 3 belong to. And what do you think? The red, the green, or the blue? Where does the negative 3 go? Goes in the red, because let's look at that. The red domain restriction says that this piece of the function is for all x's that are less than 0. Is negative 3 less than 0? Absolutely. So here's what we do with that. We say, okay, negative 3 belongs here. We're going to take it and we're going to plug it into the 2x plus 3 part of our function, because that equation goes with these x values. So this belongs to the red piece. So So we're going to take that negative 3 and plug it into 2x plus 3. And then do our math. And that will give us our y value at that part, if we had this graph. That's where the y would go. So when x is negative 3, y is negative 3. And then we do the next one. H of negative 0.001. So that's kind of funky, but it's not too bad when you think about it. It's a negative number. In this particular function, the negative numbers all belong to the same piece. Is it the red, the green, or the blue? The red, because it's everything less than 0. Basically, it's saying every negative number belongs to that part of the graph. And so if negative 0.001 belongs to this domain restriction, x less than 0, we take that value and we plug it in to the 2x plus 3. Those are corresponding with each other. So it's 2 times negative 0.001 plus 3. Take a minute on your little baby calculators. Tap, tap. I should hear tap, 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 while you figure out what that math is. I should hear tapping on the calculators. I don't hear very much tapping. Who's not tapping on my chamber calculators? $2.998. Thank you. Yes. H of 1. So now x is 1. Does that belong to the red, the green, or the blue domain restrictions? Blue, absolutely, right? Because 1 is between 0, oh, sorry. Blue, absolutely. I don't even know. Green, it belongs to the green because 1 is between 0 and 2. So now instead of plugging 1 into 2x plus 3, I'm plugging 1 into x squared plus 1 because that's the part of the function that goes with its domain restriction. So now it's 1 squared plus 1, which is 2. Yes? No, your y's could be all over the place. There's no rules about the y's. The next one, h of 2, which domain does 2 belong to, the red, the green, or the blue? Blue? Anybody think green? Anybody confused? Why are you confused? There's no what anywhere to let you know it would be the 2. There's no equal, right? So this domain restriction, the green one, says everything less than 2, but it can never be equal to 2 because there's no equal bar. The blue one has a 2 in it as well, but still, there's no equal to, right? So on the graph, if this were a picture, you'd probably have an open circle at x equals 2. But as far as evaluating it mathematically, you would just have to say that the solution does not exist because 2 doesn't belong anywhere. And then x equals 3. Does that belong to red, green, or blue? Blue. Because the blue domain restriction is all x is greater than 2. Is 3 greater than 2? Absolutely. So we're going to plug that in for x. But do you see an x there? No. So when it's just a constant number, remember that's a horizontal line where y is equal to 5 everywhere on that line. So when x is 3, what is y? 5. Okay, so that's when it's a constant, your output will be 5 no matter what your x value is, as long as it fits in that domain restriction. Right? I want you to try the next problem that's in the upper right corner. Take a minute and do that yourself. Take a moment. All right. So we've got red and blue and green. The first one, h of negative 3, where does negative 3 belong? Red, blue, or green? Red, because negative 3 is absolutely less than negative 1. So then we plug it into that equation. So it's negative x. X happens to also be negative. So much negativity on this problem. So those cancel out. 3 minus 3 is 0. Who got 0 for that one? Excellent. Okay. Negative 1, CJ, does that belong to the red, the blue, or the green? Blue. Now, I see 2 negative 1s, right? But the reason why it does not belong to the red is because the red does not have an equal. It will never actually be equal to negative 1 in the red. So it's blue, so I'm going to go plug negative 1 in for x. Well, I mean, I would, but what's the problem? There is no x. It's just a constant of 2. That's a horizontal line where y equals 2 everywhere, no matter what your x value is. So even though x is negative 1, we can't plug it into anything, but we know the output is 2. H of 0, x is 0. Hayden, which is that, red, blue, or green? H of 0. Does 0 belong to red or blue or green?
I don't know.
That's okay. We'll look at it now. Look at these. Where does the 0 go? Where does 0 fit? Blue?
I don't know.
Oh, I thought, did you say blue? Okay, it's blue. It's blue. And what does everything in blue equal? 2. Bentley, what about 1.99? Red, blue, or green? It is blue, because blue goes up to 2, right? 1.99, definitely less than 2. I mean, it's really close to 2, but still less than. So what's the answer there going to be? 2 again. Right? What, did I say wrong? Oh, that's my serial killer handwriting. I don't know. I don't even know how my brain does twos, but I know it bothers people all the time. I don't know. You're not the first person to ever point that out. Like, why did you do your 2 different? I didn't even know I did it. All right, h of 2, x is 2. Does that belong red, blue, or green? Green, right? So there's 2 2's in the domain restriction, so it could be confusing. But the one in the blue does not have an equal bar. The one in the green does. So it belongs here. We plug it in there. Let's talk about absolute value for a minute, because there's been some confusion today. Here's a few things I want to clarify for you. Absolute value does mean your answer is going to be positive. It does not mean you change stuff to positive right now. So just because there's a minus in there doesn't mean you're changing it to a positive. You do all the math inside first so you can't do anymore. You simplify it all the way. And so that's going to give me 0 inside there. And then I had several people today think that the absolute value of 0 just goes away and that your answer is 3. But it does not just go away. Whenever we say that we drop the absolute value bars, it's because we've performed the operation of the absolute value, which is this. How far is 0 from 0? 0. So the absolute value of 0 is 0, and the operation between the 3 and the absolute value is a multiplication. Okay. And what is 3 times 0? 0. And then h of 4, which domain does 4 belong to, red, blue, or green? Green. So we plug it into the green function. 3 times 4 minus 2. Do the math inside before doing the absolute value. What's the absolute value of 2? 2. And what's the operation between the 3 and the 2? Multiplication. So that is 6. Okay. Who got all those right? Very good. Proud of you. Thank you. What we're going to do now is graph some piecewise functions. What we just did was evaluate them. Means find the value and given a certain x, we were given inputs, we found the outputs. Does anybody need this up before I change the screen? Okay. So we have this piecewise function made up of 2 parent functions that have been transformed. These domain restrictions, remember yesterday when we were cutting the graphs, like vertically, we cut through them? That is what we're going to be thinking about with these things, the domain restrictions. And then these are going to be our parent graphs that we're cutting, only this time, instead of giving you the graph already, we have to graph it ourselves. So let me write these. I've got 2x plus 1, x less than or equal to 0, and then I've got x minus 2 squared minus 3 from 0 to 5. And I have been forgetting all day to ask for the domain and range, so I'm writing in this here before I forget, because otherwise I forget. Okay, so 2x plus 1. We want the piece of that graph that's to the left of 0. Now here's how I like to do these. I like to give myself a dotted line at the boundary restrictions, the same way we did yesterday, the ones we were cutting. And then I just graph the part that I need to fit inside those restrictions. Some people, though, like to graph the entire thing first and then erase what they don't need. You're free to do whatever you like as long as it's giving you the right answer. Here's how I like to do it. For 2x plus 1, I know that there's a domain restriction at 0, so I just give myself a dotted line or a light pencil through 0 to remind myself there's a boundary there. And then I just start graphing, okay? So for this linear function, we start with the y-intercept, which is what? The y-intercept is? 1. Okay. So I'm going to put a point at 1. It just happens to be on the boundary line. So I have to make a decision here. Will that point be an open circle or a closed circle? Closed, because it can be equal at 0. So I have this right here, closed circle at 0, 1. Normally when I'm graphing linears, I just go up and to the right, like this, with my slope. Up 2 over 1, up 2 over 1. And I could do that for a while, but those actually aren't the points I need, right? Because I want all the x's going which way? To the left of 0. Awesome. Thank you. Tell them I said thank you. All right. So we really don't need the points to the right. We need the points to the left. So you just do your slope in the opposite direction, right? Down to left 1, down to left 1, and connect them. Here's something I'm going to be very particular about. Students a lot of times are just a little bit lazy, and they just will graph those. Wherever they stopped dropping points, they just connect those and then they're done. Okay, but this is not an actual representation of what the function is saying. That's just a line segment. How far is this actually going to be going on to the left of 0? To infinity. So I want you to put an arrowhead on the pieces that go out to infinity. I will be circling it for partial credit if you don't. So please be sure to do your, now it looks like it curved. I'm sorry, that's going to bother me. Not a lot bothers me but on graphs because I'm not very good at them, but that would bother me. Okay, and then everything to the right of 0, I can just erase because I didn't actually need it. Still looks like it's curved. I'm sorry, you guys. So now the red stuff. This parent function is a quadratic, right? And it's going to be, I only need the piece of it that goes from 0 to 5. So I already have a little boundary line at 0, And I'm going to put one at 5 just to hold my place here. And then I start graphing. Where's the shifted vertex going to be at? Perfect. 2, -3, because it goes right 2, down 3. Now I'm just going to do there's no A value, there's no reflection. I'm just going to do my counting pattern until I have filled up the entire domain. So I'm actually going to do more than 3 points. Last unit, when we were just worried about the general shape of them, I said you could just do 3 points. But now I'm going to do more so I can fill up the whole thing. Okay. So I'm going to go to the left first. So there's no A value, so I'm going to go left 1, up 1, left 2, up 4. But in that case, it actually lands me right on top of the green dot that I already had there. And it is not included at 0. So what I'm going to do here is that half open circle that we talked about yesterday on the red side, because the points overlap. They don't always overlap, but in this case they do, and that's how you would handle it. And then I'm going to fill in the right side, but I need to go over all the way till I hit 5, so I need to count for 3, 3, 9. And at that point where x is 5, do I need an open circle or a closed circle? Closed, because it has a wiki wiki. And there we go. You try the last one while I check out my candy. Distracted. Squirrel. All right. So thank you, Matthew. So the domain is your left boundary to your right boundary, okay? What's the left boundary here? Negative infinity. And then you're just going to look for breaks. So look at all your x values as you go across. There's no breaks. There's not even a break right here because there's a closed circle. And then there's no breaks all the way to the end. So x is good from negative infinity to 5. But does the 5 get a parenthesis or a bracket? Bracket, right? And then the range is from bottom to top. What's the bottom boundary for the y values? Negative infinity. And as you go up vertically, you're looking to see if there's any breaks in the y's. So I don't see any. I don't see any. I don't see any. Here's where the green stops, but the red picks up there and keeps going. So there's actually no breaks in the y. But what's the highest y value? Is it 6? Okay. And that gets a bracket also. Okay. Now do the back while I look at my candy. The stuff. The stuff. Here we go. All right. The cube root of x plus 1 is on the domain from x all the way up to 1, but not including 1. Remember that the cube root does not go up and down. It goes left to right. Okay, it's flat. And the inflection point shifts which direction? Which way does it go? The left, how many? 1. Let's wrap this up. I've been dragging this out too long. Shush. I've been also not serious myself, so I apologize, but let's just finish. So from here it goes down 1, left 1, up 1, over 1, and it's going to cut off if you want the exact value of the cube root of 2. It is, what did I say? 1.26. So it ends up landing somewhere here. And is it going to be an open circle or a closed circle when it hits 1? Open, right? So it's going to be open like that. And how long is it going to go out this way? So you need a what? Arrow. And then the other one is a quadratic. The vertex went which direction?
Right.
Right 3, down 2. And it's graphed from 1 to 6. Both of those are included values. There's no A value. There's no reflection. So you just do your regular counting pattern. Left 1, up 1. Left 2, up 4. And that's going to be closed. It's actually not there. It's actually here. It's going to be closed there. And then you fill in your other side. And you're going to have to do your counting pattern for 3, 9. And that's going to be a closed circle because 6 is included. And then you just connect them. I'm not going to be overly particular about how they interact right there, because they don't quite join, but just do something, and if it's close enough, I'm good with that. And the domain is negative infinity. Are there any breaks in the x values? Mm-mm. Because this blue one goes all the way to 1, and then the red one picks up right at 1. And it's got a value at 2. So there's actually no break in the x's, but it does stop at 6. Does that 6 get a parenthesis or a bracket? Okay. And the range, do you see any breaks in the y values? No. So what's the highest y value? 7 with a bracket.